Well, hi there, sports fans, and welcome to another exciting edition of Physics 12. Today we're looking at lesson 3.1, which is on work, power, and efficiency. So when I say welcome sports fans, hopefully you are a sports fan. And of course this is an image of Roger Clemens when he was with the Yankees. Of course, maybe because of him you're not really a sports fan, or perhaps not a baseball fan. However, what we're going to be looking at today is work and energy, and so we're starting into chapter 3 now. So we're going to be looking simply at work done by a constant force. Work done by a changing force is a little bit more complex. They save that for university courses for the most part because it requires some further calculus in order to work with those kinds of things. So we're working mostly with forces that are constant in this course. So the definition of work then, the work done on an object by a constant force is defined as the distance that the object is moved multiplied by the component of the force that's in the direction of displacement, or what we could say perhaps is that it's in the direction parallel with the motion of displacement. So again, you can see that we're probably dealing with components, and so generally speaking, the forces are not necessarily in the direction that the object is moving to, or that it's always parallel with the direction of motion. So we have to deal with components once again, but that's pretty much what we have to get used to. So work then is defined as just simply the force that's being applied to the object in its direction of motion times the distance that it's moved. Alright, so that's just simply what work is defined as. Work is the force times the distance. Now work is not actually a vector. It does have positive and negative values. In other words, you can take work away or energy out of a system, which would be negative work. But work itself is not really a vector. It doesn't really have direction. It can be either positive or negative, but that doesn't really tell you anything about its direction, because it really doesn't have direction. So as you can see here, this would be just a typical sort of simple example of this. Person is pulling an object across the floor, pulling it with a rope, and as you can see, the rope is not being pulled parallel with the direction of motion of the object. And so therefore what we have to do again is we have to get its component that is parallel with the direction of motion. So in this case, if this angle is theta here, then we would be using the component which is F cos theta. So that it's always the component of the force that's parallel with the direction of its motion, and then here would be the displacement that the object is moved over. And so the work in this case then would be, the work to move this object from here to there would be the force times the displacement times cos of that angle, cos of theta. Alright, so that's just simply what work is. And in the SI system, Système International, in my best French accent, Système International, the units of work is joules. And so 1 joule is 1 Newton times 1 meter. And so again, this just makes sense because work is defined as force times displacement. And so it's just simply, you have force in newtons times displacement in meters, and that equals a joule. And so it can be quite simple often to derive the units then as to what the units actually are, in this case joules, as a Newton times a meter, because that is just simply what the formula for work is, which is energy. Work is energy. The energy that's added to a system or taken away from a system. That's really what work is. All right, so in In this situation here, what we've got is a person that's holding up an object, some objects that are in a bag, and is moving them through a specific displacement. However, in this case, the forces that are being applied to the object are in the y direction. However, the displacement of the object is in the x direction. So in this situation, there actually is technically no work being done on this object because the forces are not parallel with the displacement. Now, it can be argued that it takes force to move the object. However, that force is pretty much negligible because there's no friction on it or anything. The person is holding it up, and so to move an object that you're holding from one place to another, really you're not actually doing any work on it. You'd be doing work on it in lifting it up from the ground, and we will be looking at those kinds of things later on. But moving an object like this, the forces are really perpendicular. So if the force is perpendicular to the direction of motion or to the direction of the displacement, then really there's actually zero work being done on the object. So as long as this person does not lift or lower the bag, then he's actually doing no work on it. And the force he exerts has no component in the direction of motion. All right, so solving work problems, and again, so it's just a kind of a step-by-step sort of a process. Have you seen this before? Draw a free body diagram, and you'll be hearing me harp on that the entire year. Draw a free body diagram. Again, if you get all the forces and the motion and everything on there, if you get that correctly, you're more than you've mostly solved the problem already, actually, if you get your diagram correct. Okay, then choose a coordinate system, like we've done before, and sometimes we need to vary our x and y directions, which we can do. Apply Newton's laws to determine any unknown forces, and then find the work done by a specific force. And to find the net work, either you need to find the net force and then find the work it does, so find the net force, or what you can do is find the work done by each of the forces and then just add them up together. Some of them might be negative, they may be taking energy away from a system, or they might all be positive, which in other words means that they're all contributing or they're adding energy to the system. So either your net force or the net work by adding all the work together. Either way works. All right, that brings us to power now. And power is, in terms of our everyday use of the word, it's not actually very well understood by most people. So we will be providing a very specific definition of the term as it applies to physics. And the way we use the term power in science or in physics is it's the rate at which work is done. So work is adding energy to a system, force times displacement, and the power is the rate at which that is being carried out. How quickly are we adding energy to a system? That is what power actually is. And so the average power then is the work. It's just simply work divided by the time. So that's the energy that's being transferred to a system, either added to a system or taken away from a system, divided by the amount of time at which that force is being, or that work is being applied to that system. And so once again, in the Système International, the units of power are watts. So 1 watt is 1 joule per second. And again, if you look at the units here, it just simply makes sense. Work is force times distance, which is joules, and then divided by seconds. So 1 watt is 1 joule per second. And if we look at a situation here now where a person is climbing the stairs, now you can go from the bottom of these stairs to the top of these stairs in just about any kind of manner that you like. You could walk very slowly, you could run up the stairs. It doesn't really matter how you get to the top. The amount of work that you do will be the same. However, if you do it in a quicker time, that means that you are you are doing that with a greater amount of power. So power is the unit of work per unit of time. And so if you go up quicker, then your power is greater. However, the actual energy or the work done will be the same no matter if you go quickly or if you go slowly. And so that differentiates the very specific difference between the term power and work. So the difference between walking and running up these stairs is simply power. The work done would be the same. The work would be the same. The only difference is how quickly you do that. So the change in gravitational potential energy is the same from the bottom to the top of the stairs. The only difference is how quickly you do that, and that tells you the amount of power that you are using in order to do that. The last thing we're going to look at is efficiency. And efficiency is, we use this symbol here, which is called the Greek symbol eta. It has no units, it's just simply a ratio, kind of like the coefficient of friction. It also does not have any units, it's just simply a ratio. So the ratio for efficiency, it has no units, it's the Greek symbol eta, and we can determine that by the amount of output that we get from a system divided by the input. In other words, how much bang for our buck do we get from the input? How much energy do we get out of a system by putting in a certain amount? And that will give us the efficiency. We can use the ratio of work. So in other words, the work that's put into a system, the ratio of the output work divided by the input, or we could use the total energy. So the energy that we put in, compare that with the energy that we get out. Or we can use power. The amount of power that we put into a system. Let's look at the amount of power that we get out of a system. And any of those ratios, now you can't sort of mix and match. If you're starting out with work, then it has to be the ratio of output work to input work. Same with energy. It has to be the ratio of input energy divided by output energy divided by input energy, or output power divided by input power. So you can use either of those three ratios, but you can't mix and match, so you just have to be very careful with that. So that's our introduction to work and power and efficiency.